So in this podcast, I'm going to consider vectors that are functions of a parameter. Here I'm calling the parameter t, and I'm going to assume, for the sake of being concrete, that t is time. The ideas all extend to vectors that are functions of other parameters. And if I want to differentiate with respect to time my vector that depends on time, I'm going to show that from the definition of a derivative, all you need to do is to differentiate the coefficient functions and just leave the basis vectors I, j and k in place. So we take this, differentiate it with respect to time, and that is the component in that direction, etc. Similarly, if we have two vectors which are both functions of time, and I take the scalar product of them, I could calculate that in two different ways. Firstly, I could work out what the scalar product is and then differentiate it with respect to time. Or secondly, motivated by the product rule, and we're going to see it follows that way, you can differentiate the first vector with respect to time and take the dot product, the scalar product of that with the second vector, plus the first vector times dotted into the derivative of the second vector. Finally, we're going to look at the vector product, and the derivative of that is obtained very much in the same way by differentiating the first of our two vectors, crossing it with the second, and then adding to it the first vector and taking the vector product with the derivative of the second vector. So again, we could work out what the cross product is and differentiate it, or we can use this. So in this podcast, we're going to show all three of these things, and firstly, we're going to look at the initial idea of differentiating a vector. So to differentiate a vector, let's just recall the definition of the derivative. And if we're differentiating a function f of t, it's a limiting procedure. We take the function at t plus h, we subtract the function at t, and this difference is divided by h, and we take the limit as h goes to 0. So all we have to do, if we have a vector function to differentiate, so let me write out a vector function. I'm going to say it is x of t, I, plus y of t, j, and I'm going to restrict myself here to 2 dimensions purely to keep the equation shorter. You can, I hope, easily convince yourself that were you to add on to this plus z of t, k, that it would not change anything. You would get the natural extension that was written on the first slide. So this is going to be the limit as h goes to 0, 1 over h, open brackets, and I'm writing it this way because this is going to now be rather long, and just having 1 over h outside is going to make life a little bit easier for us to follow, I think. So we have x evaluated at t plus h, I, plus y, whatever that function is, evaluated at t plus h, j. So this is our vector function here, but now not evaluated at t, but evaluated at t plus h. And this is our first term here, so now we have to subtract our vector function at t. So that just means we now subtract x at t, I, and I'm going to put brackets around it, plus y of t, j. Close my brackets here, and then I want to close this bracket, so I close it as well. So what we're going to do now is to expand this bracket here, so that means there'll be a minus sign in front of this, and we'll have a minus sign in front of the y. And we're also going to clump things together, so x with x, the stuff in the I direction, y with y, the terms in the j direction. So what we're going to obtain is, this is the limit, as h goes to 0, 1 over h, open brackets, and now I'm going to open another set of brackets. It is x of t plus h minus x of t, close brackets, in the I direction. Before I write down the rest of the terms, let me just explain what we're doing here. The terms in the I direction here, there are two of them, x of t plus h and x of t with a minus sign. I've just put them in common bracket multiplying I. And similarly, the terms in the j direction, y of t plus h and y of t with this minus sign, give us plus, open brackets, y of t plus h minus y of t, close brackets, j, and then I have to close this bracket at the front, and that is everything. Now, we have to work out this limit divided by h, and this limit divided by h, and the limit of something plus something else is the sum of the limits. So it's the limit of this plus the limit of this. So what we get is the limit as h goes to 0, 1 over, x of t plus h minus x of t, all over h, and there's a common factor of I that I'm just going to pull outside. So this is this term and the limit. And then we just add to it plus the limit. H goes to 0, y of t plus h minus y of t, all over h in the j direction. And now we look at this and we see that this here is the limit of the derivative, or this limit is the derivative of x of t. So what we see is that this is d by dt of x of t in the I direction plus d by dt of y of t in the j direction. And as I said, if we had other dimensions, if we were in 3 dimensions, say, there would be another term to add on, but the basic idea would be exactly the same. So this is the derivative of x of t I plus y of t j. And really this is very much like deriving from the definition the sum rule of differentiation, that if you're differentiating the sum of two functions, then all you have to do is differentiate one and then add to it the derivative of the second. So this is our result, and one of the key ideas that came into it, of course, is that our basic directions I and j, these unit vectors, are constants and are not changed by differentiating with respect to our time parameter. Okay, so with that we'll stop and move on to the next result, which is to differentiate the scalar product of two vectors. So on this slide, what I want to do is to show that the derivative of the scalar product of two vectors, which are both assumed to potentially depend upon our parameter, is given by the derivative of the first vector here, the scalar product of that with the second vector, plus the scalar product of the first vector with the derivative of the second vector. So you are at total liberty to calculate the scalar product first and then differentiate it, or you can differentiate the vectors in this way and then take the scalar products. And if, for example, you knew something nice about, say, this particular derivative, that side might be an easier approach. It depends on the case at hand. So let's show that this is true. And for simplicity, what I'm going to do is just work in 2 dimensions. I'm going to say that A is A1 I plus A2j, and B is B1 I plus B2j. And to extend to 3 dimensions and say you had plus A3k plus B3k here, it would be very simple. It just makes the equations a little bit longer, and it's a good exercise for you to try on a sheet of paper afterwards. So let's start with the left-hand side here, calculate it, and show that it's equivalent to the right-hand side. So d by dt of a dot b, the scalar product of a and b, means the derivative of the scalar product of a1i plus a2j with b1i plus b2j. So all I've done is explicitly written out what a and b are. And now we have to take the scalar product. So this is equal to, we'll worry about the derivative afterwards, a1 b1 plus a2 b2. So we've just taken the scalar product here, and you multiply this coefficient by this coefficient, and you add this coefficient times that coefficient. And now, and I think this is unsurprising, we are going to use the product rule to differentiate these terms. So it's a sum of terms, we differentiate this, and then we add the derivative of that, and for both of these terms we're going to use the product rule. So what we obtain is, I'm going to use dot notation for simplicity, it's a1 dot b1 plus a1 b1 dot. So I've just differentiated this term using the product rule. We differentiate this, multiplying by this, and then we add this times the derivative of this. So that's given us those 2 terms here. And now we just add the derivatives of, or the derivative of this product here, and we get a2 dot b2 plus a2 b2 dot in exactly the same way. And now if we look at this, we've got 4 terms, and I think it's quite natural to clump them together in a slightly different way. So here we have a term where the a is being differentiated, and here we also have a term where part of the a vector is being differentiated. So let's put those together. And these 2 terms were differentiating bits of the b vector, so let's put those together. So what we obtain is a1 dot b1 plus a2 dot b2. I'll put it all in brackets, plus, and now I'm just writing these terms, and we have a1 b1 dot plus a2 b2 dot. And now if we look at this, we can recognize that this is a scalar product. Here we have b1 multiplied by the derivative of a1, here we have b2 multiplied by the derivative of a2, so this is equal to the scalar product of a vector with the vector b. So with the a being differentiated. So if you take this, this scalar product is going to be a1 dot the derivative of a1 multiplied by b1 plus the derivative of a2 multiplied by b2. And in a very similar way, if we look at these two terms here, we recognize that this is a, the vector a, scalar product of that with the derivative of b. So expanding that, oh, not derivative of b, the derivative of the derivative of b. Here, I need the dot. So the derivative of a dot b is equal to, from the product rule, the derivative of one of the vectors dotted into the other plus the vector scalar product of that with the derivative of the second vector. So that's that result, and as I've said earlier, it's a good idea to just check that you understand how that works for a three-dimensional vector. So with that, we can go on to looking at the vector product. So in this slide, what I want to do is to show that the derivative of the cross product, the vector product of two vectors, is given by the sum of two vector products, and in the first we're going to differentiate the first vector, so here, and in the second term we differentiate the second vector. And unsurprisingly, this is going to come, or we're going to obtain it, by using the product rule. But let's start by recalling the idea of how to calculate a vector product. So let's say we recall that A cross B can be written in the form of something that looks like a determinant where we have I, J, K, the three basis vectors in the top row, and in the next row we use the first vector here. Remember, the ordering of the terms in a vector product makes a difference. So we're going to write A1, A2 and A3. So this is telling you that my way of writing the vector A is A1I plus A2J plus A3K. And then in the bottom row we write B1, B2, B3. So this is our vector product, and that tells us that what we have is that A cross B is equal to, so to work out the I direction, we expand, as it were, across the top row. We say in the I direction we have this times this minus this times this. So that's A2B3 minus A3B2. So let me just write that down. A2B3 minus A3B2 in the I direction. And then we go to the next term, J, put a minus sign in front, and then it's A1B3 minus A3B1. So it's A1B3 minus A3B1 in the J direction, plus, and in the K direction, it is going to be A1B2 minus A2B1 in the K direction. So now we're going to differentiate this side and show that this emerges from it. Now this is a vector. It has three components. This is a vector, this is a vector. Add the two vectors together, you get a vector. And what I'm going to do is I'm going to calculate one of the components on this side and show it's equal to the sum of the components of these two vectors in the same direction, and I will leave checking that the other terms also work for you as an exercise. So let's differentiate with respect to our parameter A cross B, and I'm just going to look at the I component, these terms here, and then I'll just say plus other components for this. So what we're going to get is we're going to differentiate this and this from the product rule. So we're going to get, using dot notation, open brackets, A2 dot B3 plus A2 B3 dot, that's just differentiating the first product here, minus A3 dot B2 minus A3 B2 dot, and that's all in the I direction. And I've got a minus sign in front of both terms because there was a minus sign in front of this, and using the product rule you could write it as minus brackets plus, and I've just expanded the brackets in one rapid go. So we have this plus the two other components, the terms with J's and K's, which is left for you as an exercise. So let's now look at these terms, and you can see here we have a derivative of A, here we have a derivative of A, so just as on the previous slide we'll put these terms together, and here we have derivatives of B and B here, so we'll put those terms together. So what we get is we get A2 differentiated B3 minus A3 differentiated B2 in the I direction, plus, open brackets, the other terms, A2 derivative of B3 minus A3 the derivative of B2 in the I direction as well. So what I've done is I've taken these four terms, I've put this one and this one together here in the I direction, and then I've said that this whole set of terms in the I direction can be written as these two in the I direction plus this difference also in the I direction. So this is plus the other directions. And having done this, we're now really at the end. We've achieved what we want, because we look at this and we look at our definition of the cross product here, and we see, well, this term here in the I direction looks exactly like that if we were to put not A but the derivative of A with respect to t. So instead of having A2 we would have the derivative A2 dot. Instead of having A3 we'd have A3 dot. That's exactly what we have here. So this is, or this term here is the I component of A dot, the derivative of A, crossed with B. So this term here is the I component of that vector, and I leave as an exercise for you to check that the J and the K components also work. They do. So that's those terms. What about these terms? Well, again, looking at this, the A's are exactly the same here, but the B's have got look just like this, but they are derivatives. So this is plus A vector product with the derivative with respect to our parameter time of B. And we can see here that the I component works and the J and the K components also work if you work it out. So what we see is that as we desired, the derivative of the cross product, the vector product of A and B is given by the derivative of the first vector crossed with the second plus the first vector product of that with the derivative of the second. And it's essential here that we maintain the ordering here. This is the vector product A cross B, this is the derivative of A cross B, and this is A cross the derivative of B. You don't swap these around inside the cross product. Okay, so we've shown all three of the properties that we wanted to show, and on the next slide I will just write down a couple of exercises for you to check some of these properties. So just to practice the ideas that we've been discussing in this video, here are three exercises for you. The first is to differentiate this three-dimensional vector with respect to its parameter t. You do not need to calculate this using the definition of the derivative. You can just use the standard rules of differentiation to obtain this. Secondly, here are two vectors A and B. This scalar product is something we've proven, and let's check it by calculating this side. In other words, work out the scalar product and then differentiate it, and separately take the scalar product of the derivative of this vector with the second vector and add to it the scalar product of this vector with the derivative of this vector, and see that both sides agree. Similarly, for two vectors A and B, this relationship has to be fulfilled. Here are examples of vectors A and B. So first of all, work out the cross product and differentiate it, and secondly, work out the derivative of A and the derivative of B with respect to our parameter t, and then calculate these two vector products and add the terms together and see that you obtain this result. So I'd suggest that you pause the video and calculate these things, and then on the next slide I have just written down the solutions. So I hope this has helped you with differentiating vectors, and I hope that you obtain the results on the next slide. And to finish off, here are the solutions. This is the first solution. This is what you should obtain for both sides for the second problem with the scalar product, and this very simple result is what you should obtain for both sides for the vector product. And with that, we'll stop this video.